In Bose-Einstein statistics, today we are going to deal with a very important concept of ideal Bose gas. Actually, in this lecture, we will see that the expression for the number of particles present in a Bose gas and the expression for energy of Bose gas. When you say Bose gas, what does it mean? It means the gas or the ideal gas which obeys actually Bose-Einstein statistics, that is called Bose gas. Actually, you will see that the expression for energy and the equation of state for ideal Bose gas differs from the equation of state of a ideal gas which obey Maxwell-Boltzmann statistics. Because you know that a Bose gas is a quantum system while the ideal gas obeying the Maxwell-Boltzmann statistics is a classical system. So definitely it is obvious that the result will be different. You will see actually in this lecture what is the deviation of the equation of state and the expression of energy of the gas from the ideal gas classical value. Okay. So let us start from the Bose-Einstein distribution law and try to find what is the energy of this Bose gas and also what will be the equation of a state of that gas. As you know, according to Bose-Einstein statistics, if we consider that in a gaseous system, the energy of molecules lies between E and E plus dE, then the number of molecules possessing energy in this range E and E plus dE, in accordance with Bose-Einstein statistics, you have learned several times that this is given as N of E dE equal to G of E dE and divided by E to the power minus alpha into E to the power minus beta E minus 1. Okay, we have learned it. Actually, you know that this G of E dE, this is called density of states and it simply represents the number of quantum states in the energy range between E and E plus dE. Okay. Now, for simplicity, we write this factor E to the power minus alpha. Instead of this, you can write 1 over A. Actually, this A is called fugacity of the gas. Okay. And as you know that this beta is equal to minus 1 over kT. Okay, minus 1 over kT. So when you will substitute minus 1 by kT instead of beta, this factor will be E to the power E by kT. Okay. So N of E dE, this is given as G of E dE divided by 1 over A E to the power E by kT minus 1. Okay. Now again, you know that this fugacity of the gas A, which is equal to E to the power alpha, because we have considered that 1 by alpha is equal to E to the power minus alpha, so A will be E to the power plus alpha. And you also know that this alpha is equal to mu into beta, and where mu is actually the chemical potential of this Bose gas and beta is again minus 1 by kT. So this fugacity of the gas A is given as E to the power minus mu by kT. So the value of this A depends on the chemical potential of the gas. Okay, chemical potential of the gas. And now, as we are considering here ideal gas, and you know in case of ideal gas or perfect gas, we consider the non-interacting molecules. That is, we neglect the interaction between the molecules, and so there is no potential energy in such a gas. In fact, in such a gas, the energy means translational kinetic energy. So here, when you say that E is the energy of a molecule, what does it mean? It means this is simply the translational kinetic energy of the molecule. Okay? And you know that this translational kinetic energy E is given as P square over 2m, where P is the linear momentum of the molecule, and you know this m is the mass of the molecule. Okay? So as you can find, as we have to find the number of quantum states in energy range between E and E plus dE, denoted by this symbol G of E dE, which is also called density of states. But you have calculated this quantity several times before this lecture, and you know, first of all, we will talk about the density of states in terms of momentum, and then by using this relation E equal to P square by 2m, you can change that that quantity in terms of momentum, in terms of energy. So you can see, as you have calculated several times, if you consider that your ideal system is inside a volume V, and the molecule has a momentum lying between P and P plus dP. Okay? Then what is the value of this G of P dP, which represents actually the number of quantum states in the momentum range P and P plus dP? You have calculated this several times, so I am writing it here directly. This is, you know, equal to 4 pi V P square dP divided by h cube, where h is Planck's constant. Okay? Actually, when you say that Gp is equal to this much, 4 pi V P square dP divided by h cube, it means you are talking about the spinless bosons, or you are not taking the spin of the particle under account. So this result is valid only for a boson having a spin quantum number s equal to 0. S equal to 0. But if s is not equal to 0, then actually a particular quantum state will have how many spin state, and the different spin state represent the different quantum state. You know that if s is the spin quantum number of particle, then the spin degeneracy denoted by the symbol Gs is given by 2s plus 1. Okay? 2s plus 1. So for a given value of s, the system has 2s plus 1 spin quantum states. Okay? For example, if you take this s equal to 0, then this spin degeneracy Gs will be equal to 2 into 0 plus 1, that is 1. So this result defined in equation 3 is valid for a 0 spin particle. But if you consider that s is equal to 1, then what will be Gs? You can see this will be 2 into 1 plus 1, that is 3. Okay? So actually, if you will consider bosons having non-zero spin, then the number of quantum states between momentum P and P plus dP will be not equal to this much defined in equation 3, but you have to multiply the RHS of equation 3 by this spin degeneracy factor Gs. Then you will get the actual value of G of P dP. Okay? So G of P dP in this condition can be written as 4 pi Gs into V over h cube times P square dP. Okay? Are you getting the things? Definitely. This fact has been discussed earlier in several videos. So I hope you have an idea of this. Okay. Now, as you have seen that E is equal to P square by 2m, so you can write P square equal to 2me. Actually, now we are going to find what will be the value of G of ED. You know that value of G of DE and G of PdP are not different, both are same, because when energy is E, then momentum is P. When energy is E plus dE, then momentum is P plus dP. Okay? But only we will actually change the parameter. P will be changed in terms of E. So how we can carry out this transformation? You can see P square is 2me. So when you will take the differential, this will be 2P dP equal to 2m dE. Okay? Now let us cancel this 2 and 2. So you can see that this P dP is equal to m dE. Okay? And this dP will be then equal to m dE over P. And again you can write instead of this P equal to a square root of 2me. So dP is finally equal to m dE divided by root over 2me. Okay? And here this square root of m in denominator will cancel, and your final result is dP equal to root over m by 2e dE. So now let us substitute the value of dP and the value of P square here in this equation number 4, which you have obtained just now. So you can see that this G of E dE, this will be equal to what? 4 pi gs v divided by h cube times P square. Instead of P square, we will write 2me and dP. And dP is what? You can see it here. This is a square root of m by 2e dE. Okay? And again this root over 2 in denominator will cancel out. Okay? And this root e is also cancel out. So in the numerator there will be root 2 and root e. So this equation can be written in a simple form like this. This is G of E dE equal to 2 pi gs by v h cube times 2m divided by 3 by 2 times e to the power half dE. Okay? So this is the value of density of states, or you can say the number of quantum states in the energy range E and E plus dE. Now we will substitute this value of G of E dE in first equation. You know that first equation actually represents the number of molecules in this bosonic system having energy between E and E plus D. See this equation. This is N of E dE. And you can see in RHS there is G of E dE. So instead of this G of E dE, we will write the value which we have just obtained. Okay? So let us put that value of G of E dE. So after substituting that value, you will get that N of E dE is equal to 2 pi gs into V over h cube times 2m to the power 3 by 2 times e to the power half dE divided by A inverse 1 by A. Instead of 1 by A, I have written A inverse, see here, and e to the power minus beta E minus 1. This is the number of molecules of the ideal Bose gas having energy in the range E and E plus D. Now, if you want to find what is the total number of molecules, you will simply integrate this result with respect to E. So you can see that the total number of molecules in the gas present, which I have denoted by the symbol N, that will be given by 2 pi gs V by h cube times 2m to the power 3 by 2 integral 0 to infinity. Here energy lies between 0 to infinity. It is kinetic energy. This is actually a classical fact. Okay, and e to the power half dE divided by a to the power minus 1 e to the power minus beta e minus 1. Okay, this is the total number of molecules. Now, if you want to find the total energy of the gas, what will be the result? Already this result has been discussed while dealing with the problem of density of the states in case of Maxwell-Boltzmann statistic. As you know, that this number of molecules Ne, in fact, on average, each molecule in this N of E has energy equal to E. So energy of one molecule on average is E. So what will be the energy of N of E molecule? That will be E into N of E. Okay? And when we will integrate this result, then we will get actually the total energy of this N molecules. So the total energy of N molecules or this gaseous system is given as integral 0 to infinity E times Ne dE. Okay. Now Ne, you have defined this N of E dE in this equation 6. So use this equation 6 here. You can see only we have to multiply by this energy term E in this equation 6 and then integrate. So after multiplying by E, there will be in fact E to the power 3 by 2 and all other quantities will remain same. Okay. So you can see this result will be what? This is U equal to 2 pi GSV over H cube times 2m to the power 3 by 2 integral 0 to infinity E to the power 3 by 2 dE divided by A inverse times E to the power minus beta E minus 1. Okay. Now we will try to evaluate these integrals. Okay. And for evaluating these integrals, as you have also seen earlier, while dealing with the problem of partition function of ideal gas, same method was actually followed. You can see we consider that E is equal to epsilon times kT. Okay, or in other words, you can say that epsilon is equal to E by kT. We consider it. So as E is equal to epsilon kT, so this dE will be equal to kT into d epsilon. Okay. Now when you will change the parameter E to epsilon, the limits of E, which are 0 and infinity, they will not change, because you can see it from here that when E is equal to 0, see this result, then epsilon will be 0 by kT, that is 0. And when E is equal to infinity, you can see what will be epsilon. Epsilon is again E by kT, so that will be infinity by kT, and infinity by kT is simply infinity. So when the parameter will change from E to epsilon, the limits will not change. That will remain 0 and infinity. So you can say that this N will be equal to what? This will be 2 pi GSV times 2m kT by h squared to the power 3 by 2. Okay? Integral 0 to infinity epsilon to the power half d epsilon by a to the power minus 1 and e to the power epsilon minus 1. Okay? And when you will write the expression for U defined in equation 8, only difference will be what? Only difference will be in the power of E. So you can see when you will substitute this value of E, that is instead of E you will write epsilon kT, and instead of dE you will write kT d epsilon, then the expression for U will be like this. This is U equal to 2 pi GS V into kT times 2m kT over h square to the power 3 by 2, and integral 0 to infinity epsilon to the power 3 by 2 d epsilon divided by a to the power minus 1 e epsilon minus 1. Okay. So I think you have definitely understand what the calculation is going on. Actually, all these things you have learned earlier too. Okay. Now, here for evaluating this integral, we consider a limiting case of Boltzmann gas, and that limiting case was what? That limiting case was a is much smaller than 1. You know, when a is much smaller than 1, actually when t will be very large, t will be very large, and the chemical potential will be negative. Then you have learnt earlier that this a will be much smaller than 1. Okay. So in this condition, when a will be much smaller than 1, then we can actually neglect the higher power terms containing a, and in this limiting condition we want to evaluate these integrals, and for this, first of all, we will have to expand what will be this 1 over a inverse e to the power minus beta e minus 1. Okay. Or in other words, you can say a inverse e epsilon minus 1. In fact, our aim is to first of all evaluate, see here, 1 over a inverse e to the power epsilon minus 1. It means you can say that first of all we have to expand a inverse e to the power epsilon, this is a inverse, minus 1 to the power minus 1, and then you can evaluate these integrals. So let us see, this is just a binomial expansion. You can see this is 1 over a inverse e to the power epsilon minus 1. And this can be written as you can see, a inverse e to the power epsilon minus 1 to the power minus 1. Now, take this a inverse e to the power epsilon as a common factor. Since minus 1 is power on whole, so when it will be outside of the bracket, the term will be a into e to the power minus epsilon. Okay? And the first term will be 1, and second term the second term will be 1 over a inverse e to the power epsilon and whole to the power minus 1. Now take this a inverse e to the epsilon in numerator, that will be in fact a times e to the power minus 1. Okay? And so now you know that this 1 minus x to the power minus 1, this is actually equal to 1 plus x square plus x cube and plus so on. Okay? But as you can see, if x is much smaller than 1, in fact in that condition this can be approximated like this. This is 1 plus x only, because all the terms of higher power will be negligibly small. And this is the case here. You can see that we have assumed that in Boltzmann limiting case, this a is much smaller than 1, so the higher terms will be neglected. Okay? And we will write simply 1 plus x. Okay? And you can see at the place of x there is a into e to the power minus 1. So this is simply a into e to the power minus 1 into 1 plus a e to the power minus 1. I have mentioned here that neglecting the higher order terms. Okay? So in fact once you have expressed this factor like this in terms of a power series, So now you can write the expression for this n. You have seen that n is equal to 2 pi gsv times 2m kt over h square to the power 3 by 2 integral 0 to infinity, and see the factors inside the integral here. So sorry, the page has been turned, but this will be just okay. As you know, this is a usual feature of my iPad, so don't mind it. Okay, now it is correct. So see here, this epsilon to the power half d epsilon, this will remain at is, and 1 over this much, we have already expanded it. So write that expansion here, and you can see after writing this, the result will be integral 0 to infinity d epsilon epsilon to the power half times a e to the power minus epsilon times 1 plus a e to the power minus epsilon. Okay, and now we will solve this equation. You can see actually this can be written as 2 pi gs into v times 2m kt over h square to the power 3 by 2. Okay, and here integral has been operated on both of the terms, and you can see in first term a has been taken outside of the integral, and there is e to the power minus epsilon times e to the power half d epsilon, and in second term here will be a square e to the power minus 2 epsilon epsilon to the power half d epsilon. Okay, now for simplicity here we multiply these integrals by a factor 2 by root pi. Actually this 2 has been brought from here, this 2, but this root pi has been written extra, so you will have to multiply by root pi in numerator 2. So when you will multiply this pi by root pi, this will be pi to the power 3 by 2. So I have written this pi inside the bracket and put on it the power 3 by 2. So you can write this expression as gs into v 2 pi m kt over h square to the power 3 by 2. Okay, and this is 2a by root pi times this integral and plus 2a square by root pi times this integral. Okay, now you know actually by the use of the concept of gamma function, the value of this integral 0 to infinity e to the power minus epsilon times epsilon to the power half d epsilon, its value is pi over root pi over 2. Okay, and you can also say that this is root over pi by 2 into 1 by 1 to the power 3 by 2. Okay, plus 2a square by root pi and integral of this e to the power minus 2 epsilon to the power half from 0 to infinity. By the same concept of gamma function, its integral is root pi by 2 into 1 by 2 to the power 3. Okay, and you can see this root pi and root pi will cancel, this 2 and 2 will cancel. Okay, so why I have multiplied by this factor 2 by root pi, now you can understand. This is for simplicity. Okay, so in first term there is only a, and second term is a square times 1 by 2 to the power 3 by 2. So you can write this n as gs into v times 2 pi m kt by h square to the power 3 by 2 times a 1 plus a by 2 root 2. Okay, so in this way, in terms of a or as a function of a, we have calculated the total number of molecules present in this gas. Okay, now in the similar manner, when we will actually use the concept of gamma function and if we try to evaluate this integral, what will be our result? I have written actually it here directly. Okay, so u will be equal to 2 pi gs v into kt times 2 m kt by h squared to the power 3 by 2 integral 0 to infinity d epsilon epsilon to the power 3 by 2 a into e to the power minus epsilon times 1 plus a into e to the power minus epsilon. Only instead of epsilon to the power half, here there is epsilon to the power 3 by 2 and other factors inside the integral remain same. So by the same concept of gamma function, it is found that this result will be what? Following these steps exactly. I have written this result directly because we have already discussed in this above paragraph in detail. So you can write directly and you can remember it. U is equal to 3 by 2 kt times GSV into 2 pi mkt by h squared whole to the power 3 by 2 into a times 1 plus a by 4 root 2. This result I have written directly on the basis of the above result. Okay. So n and u both you have calculated. Okay. Now from this equation which actually defines the value of n, you can find the value of this a. So see this result and you can see there will be a simple algebra and you can write a is equal to n by gv times h square by 2 pi mkt to the power 3 by 2 into 1 plus 1 by 2 root 2. 2 root 2 means 2 to the power 3 by 2. Instead of that, I have written 2 root 2 into n whole to the power minus 1. Okay. And now, as a is equal to this much, when you will actually neglect this a, then this a will be almost equal to this much, almost. Neglecting the second term. In fact, when this will be expanded, this will be 1 minus 1 by 2 root 2 into a. 1 minus x, higher term will be neglected. And so, when a is much smaller than 1, we can neglect this second term in comparison to 1. In that condition, a will be simply equal to this much. This will be n by gs into v times h square by 2 mkt whole to the power 3 by 2. So instead of this quantity a, actually it has been written that this is 1 minus 2 root 2 times this much. Okay, this has been written. So in this way we have obtained the approximate value of this a. Okay. Now this value of a will be substituted in the equation number 12. You can see this equation 12, you can see it here. When you will substitute at the place of this a the value obtained there, then you will get the value of u. And you can check it. I have not done the complete algebra, but you can do it. So doing all the algebra there, then you will find that u is equal to 3 by 2 nkt into 1 minus 1 over 4 root 2 n by gs into v times h square by 2 pi mkt to the power 3 by 2. Okay. Now this expression of energy you can see has two terms in RHS. First term is what? This will be 3 by 2 nkt into 1. That is first term is 3 by 2 nkt. And can you remember what is this 3 by 2 nkt? This is the energy of a perfect gas or a dilute gas in Maxwell-Boltzmann statistics. That is the gas obeying the classical statistics, you know, has an energy 3 by 2 nkt at temperature T. So actually the first term in the RHS of this expression for energy U represents the energy of an ideal gas in case of Maxwell-Boltzmann statistics or in case of classical statistics. So in this condition, the second term will represent the deviation, the difference of the energy of Bose gas from the classical gas. Okay. So the second term will be what? This will be 3 nkt into minus this much. This is the difference between the energy of a Bose gas and the ideal classical gas. So this difference is equal to what? This is minus 3 by 2 nkt times 1 by 4 root 2 into n by gs into b into h square by 2 nkt whole to the power 3 by 2. Okay. This is the difference. This is the deviation of the value of energy of a quantum gas, that is a gas obeying the Bose-Einstein statistics from the gas obeying the Maxwell-Boltzmann statistics. Both gases are ideal. Both are in same physical condition. But one gas obeys Bose-Einstein statistics and another obeys Maxwell-Boltzmann statistics. Can the energy of two gases will be same? Answer will be not. No. Answer will be no. Their energy will differ, and that difference is equal to this much. This is the difference. Actually, the energy of the Bose gas will be smaller because here the difference is negative. Okay. So this is the required correction due to the deviation from the classical behavior, you can see. Now, you know that the relation between the macroscopic parameter PV with the energy U of the gas. Definitely you have studied in the classical kinetic theory of gases that PV is equal to 2 by 3U. Remember this result. This you have studied in your lower classes. Now, as you have obtained the expression for U for a Bose gas here, you can see in equation 14. So if you want to write the expression for PV, you will have to substitute this value of U there. So substituting that value of U, you can see your result will be PV equal to nkt into 1 minus 1 over 4 root 2 into n by gs into v into h square by 2 pi mkt whole to the power 3 by 2. Okay. And this is the equation of a state. But you know the equation of a state of an ideal gas obeying the classical statistics, that is equal to PV barabar nkt. Here the first term is actually nkt, but the second term is not 0. So you can see that the equation of a state of a Bose gas is not exactly same as that of a classical ideal gas. It is different from that. What is the difference? Difference is nkt into 1 over 4 root 2 into n by gs into v into h square by 2 pi mkt whole to the power 3 by 2. This is the difference. This difference is similar to the difference of energy. So I have mentioned it here. You can see that PV equal to nkt. This is the equation of a state of ideal Maxwell-Boltzmann gas. You can see. And the deviation of this equation of a state from the classical perfect equation is equal to this much. Okay. So this correction depends on the value of this quantity. This depends on n by gs into v into this much, because nkt is already present in the classical equation too. Okay. Now you can see this quantity will be very small, then this can be neglected. But when this will be very small, you can easily see that if n by v is very small, if this tends to, let us say, 0, and this T is very large, very high temperature, then this number will be actually much smaller than 1. Okay. So n by v times h squared divided by 2 pi m kt to the power 3 by 2. If it is much smaller than 1, then this correction term can be neglected and the equation of a state will be same as that of a classical gas. Okay, as that of a classical gas. Actually, here I have taken this Gs equal to 1. Can you say Gs equal to 1 for what? You know, Gs is equal to 1. It means, you know, Gs is equal to, in fact, 2s plus 1. Gs, which is spin degeneracy, you know, that is equal to 2s plus 1. Okay. Gs equal to 2s plus 1. And this will be 2 into 0 plus 1, then it will be 1. So this Gs will be 1 only when you take this s equal to 0. That is, for a spinless particle, Gs is equal to 1. And the correction term, if it is much smaller than 1, then it can be neglected. But when this will be much smaller than 1, as I have told you earlier, that for this should be much smaller than 1 only when n by v is very small and t is very large. When n by v is very small and t is very large, actually in that condition this correction factor will tend to 0. And in that condition, the expression for energy will be what? You can see. The expression for energy of a Bose gas, you can see it from here. When you will take this second term almost 0, then u will be only equal to 3 by 2 nkt. Only 3 by 2 nkt. Okay? And this PV will be then equal to nkt. And you know that both of these results are classical results. Okay? This is the energy of a gas, perfect gas, obeying the Maxwell-Boltzmann statistics, and this is equation of a state of a perfect gas obeying the classical statistics. Okay? So you can see that for this n by v, when n by v is very small and temperature is very large, in that condition, the energy expression and the equation of a state of a Bose gas is exactly same as that of a gas obeying the Maxwell-Boltzmann statistics. It means at in fact a high temperature, and when the number of molecule in the gas is very small, that is gas is very dilute, very rare. In fact, in that condition, a Bose gas will behave as a Maxwell-Boltzmann gas at high temperature. But what will happen when the temperature will be lowered? In fact, when temperature will be small, then this correction factor cannot be neglected. This will be large, and in that condition, Bose gas will be actually different behavior from the classical gas. And in that condition, you must take this correction factor under account. Okay? So, if a perfect gas, your aim is to use a perfect gas as a classical gas. What you will take? What you will impose the condition? The condition imposed will be the number of molecules per unit volume should be very small and temperature should be very large. Then the gas will behave just as a classical gas. But when temperature is lowered, then actually the molecules come closer, the gas becomes dense, and there will be an overlapping of wave packets, and the quantum effect will dominate and the gas will behave as a Bose-Einstein gas. Okay? So this was all about the concept of ideal Bose gas. I hope you have definitely enjoyed this lecture.